All right, today we're going to be looking at three different concepts, and a lot of times these concepts get confused for each other. So we want to clarify the difference between the three examples, and then we're going to start using these examples today for our problems that we work on. So the first one says the instantaneous rate of change. Most of us are very familiar with that. That's just the derivative. And so you can see the example over here. The slope of the tangent line at a point is the derivative at that spot. So at x equals a, we write it f prime of a. So we're going to do two more things that are kind of like that. So let's have a look. The second one would be the average rate of change. So it's not the instantaneous rate of change, but it's the average rate of change. So instead of being just at one point, it's going to be the slope of the line that goes through 2 points. So you see the slope of that blue line is going to be the instantaneous slope, and the slope of that red line is going to be the average rate of change. It's almost like an average slope over an interval of time, where the blue one is kind of like a slope at just an instant in time. A lot of you might just recognize this as just the slope of a line. So, I mean, it goes through 2 points. It's the kind of slope we've done ever since we were in middle school. We're giving it kind of a weird name, average rate of change. And the important thing about that is it's going to be over an interval of time. So from A to B. So you usually need 2 points to calculate that. It's just going to be the change in the y over the change in the x. That's basically what it is. We do have one more that's kind of new. Let's have a look at that one. And again, we're just trying to show the difference between these three things. So when you see average value, you know what to do. Now, the way we usually see average value is they might ask for the average temperature, they might ask for the average number of people in line, or they might actually say average value, which makes it even easier. When they say average value, this is what we're going to be doing. We're going to find the integral from a to b of that function, but then we have this 1 over b minus a in front of it. And I have a couple pictures over here to kind of show you what's going on. Let's look at this blue one first. You can see this blue region is almost like water. And if this water was to settle, what height would it land on? And that is your average value. So this green bar here is kind of like my example of where the water would settle. Right now it's kind of like a wave coming through here. But if it was like a fish tank, and these were the walls of the fish tank over here, the A and the B, where would the water settle? You can see there's a little bit of the wave is above, a little bit's below. But if you just let it settle for 5 minutes or so, it would settle along this green line here, and that is the average value of that function. Here's an example of that right now, almost the same thing. Here's the actual function here. And if we're going from A to B, what is the average value? Well, this is an example of the water settling. It would settle at this line right here that we're calling C. So that would be your average value, C. And again, the way that you do it is you do the integral of the function that they're talking about. So if they say find the average value of f, then you do the integral of f. There's just one extra piece. This part right here, this 1 over b minus a, that's how you get the average value. Now, it's not the average rate of change, even though it has the word average in it. The average rate of change, if we go backwards, that was just the slope of a line. And we're talking about a line that goes through 2 points, just like we always did a long time ago. You calculate it by doing the change in the y over the change in the x. If we want the slope of a line that just goes through 1 point, let's back up one more step. That would be the instantaneous rate of change. And that's just the derivative, and you plug in the x value. So these are the three things that we're going to do today. Let's go ahead and look at our first example. Now for this homework, we're doing homework number 91. The first example is the hardest one out of all of them. Don't ask me why. This should be the last example. You might remember this example. We had to figure out what the volume was. We have a cylinder where the radius is always 10. So we know the area of the base is going to be pi r squared, but r is always 10. So that gives us 100 pi. That's just the base. And then the height is some function s that we have no idea what it is. So we're just going to put an s there. And so this is the volume of the water inside the cylinder at any time t. You'll notice that the units are millimeters cubed. Now for the question that we're going to do today, it says find the average rate of change of s on the interval from 0 to 60 days. You'll notice the units for time are days. Now what we need to do is we need to do the change in the y over the change in the x. In this case, the x is time. So we are going from 0 to 60. Those are kind of like your x values. So we're doing 60 minus 0. But the top is supposed to be s of 60 minus s of 0. And the big problem here, and the reason why this one's so tricky, is that we don't have s. We don't have the s function. So how are we supposed to find s of 60? How are we supposed to find s of 0? Well, there's a trick. There's one way we could do it. We have s prime. And I'm sorry to give you the trickiest one first. But we have s prime. And we know that if we do the integral of a derivative, let's do it right here, the integral of the derivative, that the integral and the derivative are basically going to cancel each other out. Our final answer is just going to be this function evaluated at 60. So there you go. And then minus, and then the same function evaluated at 0. So there you go. That's sitting right here. So that's a really tricky one. So the way that we get the top is just by doing the integral from 0 to 60 of s prime of t. That's a tricky one. I don't think you'll ever figure that one out on your own. All right, let's go ahead and look at some normal ones because this was a really tough one here. This is kind of like a challenge question here. Okay, for number 2, this one's not so bad. It just says find the average value of f. So that's easy. It's just the integral of f. And they want you to find the average value from 0 to 30. So our bounds go from 0 to 30. And then in front of it, we have to put a 1 over b minus a. So we have to put a 1 over 30 minus 0. And that's pretty much it. This is basically just a calculator problem. So you would just plug this in a calculator. Today, I'm not actually showing you what the f function is in this video because we're really just paying attention to the concept. So I know everybody can just type this in a calculator. It's not that big of a deal. But let's talk about the units for a second. Anytime you do the average value of a function, you're going to have the same units as that function. So if the function has units of cars per minute, then the average value should also have the same exact units, cars per minute. Let me show you why that happens. Well, over here, we're dividing by b minus a. And both a and b are units of time. So in this case, those units are minutes. So really the units here would be minutes on the bottom. So this piece here is giving us 1 over, and then the minutes would be on the bottom. The middle piece has units of cars. Let me explain why. The f function has units of cars per minute, and then dt is change in time, and the time is minutes. So you're going to cancel the minutes from the dt with the minutes from the cars per minute. So that's why this piece has units of cars. So if we're paying attention to the units, we have 1 divided by minute here. We have cars over here. And if you multiply those two things together, you're going to get cars per minute. So that's kind of tricky as far as the units goes. This is a tricky explanation here. But just remember, anytime you do the average value of a function, it's just going to have the same units as whatever that function is. So f had units of cars per minute. So when we do the average value of f, we're going to also get cars per minute. So you don't need to do this calculation every time. If you're doing the average value of a function, it's going to have the same units as that function. You just copy that down. Remember, the number answer is just something you type in your calculator. All right, let's take a look at number 3. Okay, so this is the exact same problem as number 2. We're using the exact same function and everything. But instead of doing the average value of f, we're doing the average rate of change of f. So it's kind of like the derivative of f, but it's on an interval of time. So it's kind of like the slope of a secant line. So this is kind of like when t is 0. And this is kind of like when t is 30. We have these 2 points. Now, since this is kind of like a derivative, we're going to get one more unit of time on the bottom. Think about it. When you do the derivative of something, you're doing d dt of that thing. So right now, our thing is f. And f has units of cars per minute. But because we're doing d dt of that, we have a dt right here, which is kind of like an amount of time. So that's why we're getting an extra minute on the bottom. So it's going to be cars per minute squared. Now this is not really a derivative because a derivative would be a slope at an instant in time. but I'm saying it's kind of like a derivative. It's just a derivative over an interval of time. And again, that's the reason why we're getting a squared down here on our units. It's because it's kind of like a derivative. All right, let's have a look at number 4. Okay, for number 4, it just says find the average value of L. Now there's one extra little challenge piece in here. They want you to find it when L of t is greater than or equal to 150. With our graphing calculator, we're not actually going to solve this inequality. What we're going to do is we're going to solve the equality. So we want to know where it's equal to 150 first, and then we'll go from there. Now this does look like it's a trig function. It keeps going up, and so it's probably going to have an infinite number of answers. So what we're going to want to do is just solve it on our interval. So we're going to evaluate it from 0 to 18, and that will give you the A and the B value. Remember, you want to store those values in your calculator so that all you have to do is type A to represent the big long decimal, and then just type a B to represent the other big long decimal. Okay, again, we're doing the average value of L of t. So average value of L of t is just going to be the integral of L of t. And then in front of it, you're going to put 1 over b minus a. Remember, your integral goes from a to b. And so the only thing that makes this one a little bit difficult is you have to find the a and the b value. That's what makes this one tough. Otherwise, just a basic example of finding the average value of L of t. What I would probably do is when you get those critical numbers a and b, because that's where L of t would equal 150, what I would do is I would just test in between. When you plugged in any time between A and B, you probably would get a number that's more than 150. So let's just say 160, for example. And then if you plug in a number that's more than B, you're probably going to get like 140 or 130 or something that's less than 150. And the same thing on the outside over here. You probably would get like 130 or some number that's less than 150. And that'll tell you that this is the interval where L of t is greater than or equal to 150. Because that's where it wants you to find the average value of L of t. So the hard part of this one was finding the A and the B value. So that's pretty tricky. And if you want to pause the video, you can see why the units would be cars per hour. Again, those are the units of L of t, so you could just match the units. You don't have to sit there and calculate it every time. All right, let's look at number 5. Number 5 wants us to find f prime of 14, so that's an instantaneous rate of change. But we don't have the equation of this line. So what we're going to do is we're going to find the slope of that green line, because every point on that line would have the same slope. So the point right here, when t is equal to 14 minutes, the slope would be the same as any other point on that green line. So over here, we're doing the slope of a secant line, because we know the slope of this tangent line is going to have the same slope as the slope of that secant line. So this is a weird one, because to find an instantaneous rate of change, our calculation is an average rate of change. Kind of a weird thing. So again, it's just change in y over change in x. Remember, in this case, our x's are actually t's, they're times. And you can kind of reduce it and you get your final answer. All right, let's go to number 6. Okay, for number 6, we're going to add some value of c to this f function over here, so that the average value of the function is 17 calories per minute. And it's just on the interval from 12 to 20. So one way you could do it is you could just figure out what the average value is right now. Let's do that. We're going to do the integral from 12 to 20 of this f of t function. And in the front, we have to do 1 over 20 minus 12. Now to find this value, you just add up these areas over here, and you would get 108. And then in the front of it, b minus a is just going to be 8. So this is giving us a 1 over 8 times 108. So that's going to reduce to 13.5. So right now, the average value on that interval is 13.5. We want it to be 17. So we need the entire function to go up 3.5. So our c value needs to be 3.5. And I would say that's probably the easiest, fastest way of doing it. There is one more way we could do it. We could do, instead of the integral of f, we could do the integral of f plus a constant and say, well, we want it to equal 17, and then we solve that one. So let's go ahead and solve this equation now. We should get the same final answer. If you look on the right, this is the one that we just did. We did it kind of the fast way. we just figured out, all right, what is the average value right now? Average value is 13.5. So if we want it to be 17, the c would have to be 3.5. So let's do it the longer way. We got to solve the equation. We're going to first break this integral into two smaller pieces. We're going to get rid of the 1 over 8 by multiplying both sides by 8. So the right side is going to become 17 times 8. We know the value of this one is 108. We did that on the previous page. And then the integral of c would normally be like c times x, just a number times x, but this is dt, so we have a t inside there. And so we just need to plug in the 20, and then minus, and then plug in the 12. So we're going to get 20c minus 12c, so that's just going to be 8c. And so we subtract 108 from both sides, and then divide by 8, and your final answer is the same thing. It's going to be 3.5. You got the same final answer either way. Okay, for number 7 and 8, we're doing the same example. It's just going to be a slightly different question. So you can see here we have the time is hours, and L of t is measured in people. And here it's asking us to estimate L prime of 2. Now what we're actually going to do on this one is we're going to say, all right, well, when t is 1 and when t is 3, the curve might do something like this. Just as an example, it might do something like this. We're trying to estimate the slope of this tangent line here in blue. And the way that we're going to do it is we're going to calculate the slope of this secant line in green. The slope of those two lines are pretty close. So this is an example where we're estimating the slope of a tangent line by calculating the slope of a secant line. So that's what you see over here. We're going to do the change in y over the change in x. Remember, our x's are t's in this example. And because we have 1 and we have 3, that's the best way to estimate the slope at 2. So they give us the y values, we can plug those in, and after reducing it, we're just going to get 10 people per hour. Remember, if L of t has units of people, then L prime would have units of people per hour. Just has one extra unit of time on the bottom. All right, let's look at our last example. For number 8, they want us to use a trapezoid sum with 3 subintervals to estimate the average number of people waiting in line during the last 5 hours. So the last 5 hours would be from t equals 4 all the way to t equals 9. Now, if we wanted to find the average number of people waiting in line, well, L of t tells us how many people are in line. So we want the average value of that. So we're going to do the integral from 4 to 9. And then in the front, we have to do 1 over 9 minus 4. And it does ask us to use trapezoids to estimate this integral. So that's what you see down here. We're using values from the table, and we're estimating this integral by using 3 trapezoids. And we're just calculating them separately. So the width of the first one is 3, and then here's your average height. The width of the second one is 1, and then here's your average height. And the width of the last trapezoid is 1, and here's the average height. The b minus a gives you a 5 on the bottom over there. And after reducing everything, you do get 113.8 people. Of course, you can't have 0.8 people, so usually they tell you to round to the nearest person. So you probably would have 114 people as your final answer. I also want you to notice that there's only 1 decimal of accuracy, but that's because that's the exact value that we got. So you don't need to put 3 decimals of accuracy if this is the exact answer you got. So this is not a rounded number, and so that's why we're only putting 1 decimal of accuracy. And that's it. Now it's time to practice our examples.